Good evening to all. Myself, Navneet Krishnan, teaching GATE in iitiansgateclasses classes from 2016 onwards. And right now, I am working as a manager in one of the company named Yotek Systems LLP, where we are designing drones, manufacturing designing drones for different sectors. In this class, we'll talk about client performance. In this class, we'll talk about client performance. If you have any doubt in between, you can stop me in between. Yeah. First, to start, we have to know what are the forces acting on the airplane. First, if you see, this is the thrust force which is acting on the engine center line. Thrust is acting at the engine center line, which is acting at an angle alpha t to the flight path. This is the free stream velocity direction. So it's at an angle alpha t to the flight path. Then your lift and drags always acts parallel and perpendicular to the free stream velocity direction. The force acting perpendicular to the free stream velocity direction, that is your flight path, is your lift. Force acting parallel to the free stream velocity direction is called as drag, which is opposite in motion. The force which is acting perpendicularly downward is called as weight. All these forces act at the different points, but here we are not considering any moment balance. Here we are considering only force balance, force equilibrium. That's why all the points I mentioned in a singular points. But in reality, lift and drag acts at the aerodynamic center, thrust acts at the engine center line, weight acts at the CG location. The angle between flight path and the chord line of the wing is called as angle of attack. The angle between the horizontal axis and the flight path is called as climb angle gamma. In some textbooks, they have used theta. Climb angle gamma. So these are the four aerodynamic forces acting on the airplane. Four forces acting on the airplane. One is lift, drag, thrust, and weight. Now, if you see, I draw a line parallel to the lift axis and perpendicular to the horizontal axis, which is called as which is the weight. Weight is acting perpendicular to the horizontal axis. So, if the angle between flight path and the chord line is the angle between flight path and the horizontal axis is gamma, we have drawn a line perpendicular to the horizontal axis, that is your vertical axis, and a line perpendicular to the flight path. If this angle is gamma, this angle is also called as gamma. The angle between the vertical axis and the perpendicular to the flight path is also gamma. Any doubt here? Because if you understand this diagram only, we can proceed further. So, the four forces acting on the aircraft is lift and drags, acts perpendicular to free stream velocity direction, free stream velocity direction. Lift acts perpendicular to the free stream velocity, perpendicular to the free stream velocity direction. Drag acts parallel to the free stream velocity direction. Weight acts at CG, center of gravity location, and thrust acts at engine center line. These are the four forces acting on the airplane. Now we'll try to resolve these forces parallel and perpendicular to the free stream velocity direction. According to Newton's second law of motion, parallel to, if we resolve forces parallel to the free stream velocity direction. Now if you see here, if I resolve everything parallel to the free stream velocity direction, what happens? Towards the angle is called as cos, t cos alpha t. Okay. Thrust when it is resolved towards the flight path, it is t cos alpha t minus drag, which is acting opposite to the direction, minus away from the angle is gamma, sine gamma, away from the angle is sine. So when weight is resolved, it will create W sine gamma here. So W sine gamma equal to mass into linear acceleration dv by dt. When I resolve forces perpendicular to the free stream velocity direction, so what happens? This is the perpendicular to the free stream velocity direction. Lift plus when I resolve thrust, it forms away from the angle is called as sine. So t sine alpha t towards the angle is called as gamma, cos. So it is opposite to the direction of lift. So minus w cos gamma equal to mass into centripetal acceleration, where rc is the radius of curvature, where v square by rc is the centripetal acceleration. So when we resolve forces parallel and perpendicular to free stream velocity direction, these are the two equations of motion. Any doubt on this part? So these are the two equations of motions. T cos alpha t minus w sin gamma minus drag equal to mass into linear acceleration. Lift minus w cos gamma plus t sin alpha t into mass and equal to mass into centripetal acceleration, that is v square by rc. Now for unaccelerated flight, if I take, for unaccelerated flight means there is no acceleration, that means linear and centripetal acceleration if we consider equal to 0, then the equation becomes t cos alpha t minus w sin gamma minus drag equal to 0, lift minus w cos gamma plus thrust sin alpha t equal to 0. In general, alpha t also, in general, thrust also acts along the engine central line. Thrust also acts along the engine center line. Sorry, acts along the flight path direction. In general, thrust also acts along the flight path direction. In very rare cases, it is slightly at an angle alpha t to the flight path direction. So, if that case, when the thrust is acting along the flight path direction, so alpha t will become 0. When alpha t becomes 0, when we substitute alpha t is equal to 0 in this equation, so this becomes thrust minus w sin gamma minus drag equal to 0, lift minus w cos gamma equal to 0, because sin 0 is 0, cos 0 is 1. These are the two equations used for your climb performance. Okay. So this figure already we have explained. So if I write the two equations of motions for climbing flight, thrust minus w sin gamma minus drag equal to 0, lift minus W cos gamma equal to G. First, we'll take the second equation, lift minus W cos gamma equal to 0. So, if I rewrite lift equal to W cos gamma. If I take weight on the other side, it is lift by weight equal to cos gamma. Lift divided by weight is called as load factor N. Lift divided by weight is called as load factor 1. For climbing flight, the load factor C cos gamma will become only cos gamma will become 1 when gamma equal to G. Okay. Cos gamma can become uh, 1 when cos 0 is 1. Okay, that means when it is having a level flight condition only, cos can become 1. When gamma becomes 90 degree, cos 90 degree will become 0. So when the aircraft is, let us assume the aircraft is flying this way, that is when gamma becomes 0. So thrust is balancing your weight. So there is no need of any lift. It is in general physics, Rishi. When we resolve forces perpendicular to free stream velocity direction, perpendicular force always is equal to mass into centripetal acceleration. Now, here lift is becoming 0, so thrust is balancing your weight, which means this is not a climbing flight where gamma is equal to 90. So gamma should be in between 0 and 90 degree for climbing flights. If gamma is equal to 0, then it is in the level flight. So lift is balanced by weight, thrust is balanced by drag for level flight. So gamma equal to 0 means it will enter into gamma equal to 0 means it will enter, if this gamma is equal to 90 degree, here gamma equal to 0 means it will enter into level flight. So for all climbing flight, the load factor will be always less than 1. For all climbing flights, the load factor will be less than 1 because cos gamma will be always less than 1, because for climbing flight it should be between 0 and greater than 0 and less than 90 degree. So for that cases, load factor is always less than 1 for climbing flights. Next, the first equation, if I take thrust minus drag, if I take W sin gamma on the other side, it will become thrust minus drag equal to W sin gamma. So thrust minus drag divided by weight equal to sin gamma. If I multiply both sides by V infinity, so thrust into V infinity minus drag into V infinity equal to V infinity sin gamma divided by weight. This is your power available. This is your power required. Power available minus power required divided by weight is equal to V infinity sin gamma. V infinity sin gamma is the rate of climb. V infinity sin gamma is the rate of climb. So this is your free stream velocity direction. So the horizontal component of velocity will be V infinity cos gamma. The vertical component of velocity, the vertical component of velocity is called as V infinity sine gamma, which is your rate of climb. V infinity sine gamma is your rate of climb. As forces are resolved, velocity also resolved into two components. One is horizontal component of velocity, one is perpendicular component of velocity. Towards the angle is called as cos, away from the angle is called as sine. Okay. So rate of climb is nothing but power available minus power required divided by weight. This thrust into velocity is also called as thrust power. Drag into velocity is also called as drag power. Okay. Now, this is how your aircraft is climbing at an angle gamma. I already told you the horizontal component of velocity is v infinity cos gamma. The vertical component of velocity is called as v infinity sine gamma. Vertical component of velocity is called as v infinity sine gamma. Initially, the aircraft was at an altitude h1 at time t1. The aircraft started climbing. At time t2, it has reached an altitude h2. So rate of climb is nothing but rate of change of altitude with respect to time. Rate of change of altitude with respect to time. So the net change in altitude is h. The total time the aircraft in climbing is endurance. So h divided by endurance is equal to v infinity sine gamma. So that is nothing but your rate of climb. So already we know that rate of climb is nothing but power available minus power required divided by weight. So power available minus power required can be called as excess power. So excess power divided by weight is called as a rate of climb. Any doubts? If you have any doubt, you can stop me there. So some part where you didn't understand, you can ask me to repeat it. So I can able to repeat that. Now, what is the condition of maximum rate of climb for a piston engine aircraft? This is your power required curve. This is your power available curve. So rate of climb is nothing but power available minus power required divided by weight. For rate of climb to be maximum, your power required should be minimum. Because power available depends upon your engine selected. Once the engine is selected, for that particular engine, what is the maximum rate of climb? The maximum rate of climb depends upon power required minimum. Power required minimum condition is CD naught equal to 1 by 3 CDI. The CD naught is your parasite drag coefficient. CDI is the induced drag coefficient. CD naught equal to 1 by 3 CDI is nothing but your power required minimum condition. If I fly at this condition, my aircraft will have maximum rate of climb for a piston engine aircraft. Okay. My aircraft will have. Then, if the power required is minimum, what happens? Already there is a power available. So, available minus power required minimum will have the maximum excess power. Yes. Power required is minimum means the differential quantity will be maximum quantity. So, maximum excess power divided by weight is the called as rate of climb max. Okay. For jet engine aircraft, we always measure performance in terms of thrust rather than power. So, in jet engine aircraft, this differs. The condition is not power required minimum. So, we'll derive the condition for what is the maximum rate of climb for a jet engine aircraft. So, rate of climb, we know that it is nothing but thrust minus drag divided by weight into free stream velocity. For steady level flight, lift equal to weight. For climbing flight, it is lift equal to W cos gamma. So, lift is nothing but CL into half rho V square S, that is equal to W cos gamma. So, velocity is nothing but root of 2W cos gamma divided by rho S CL. I keep velocity on one side, remaining all the parameter I take it on the other side. For gamma less than 30 degree, less than or equal to 13 degree, generally cos gamma will be approximately equal to 1 only, because it will be around 0.99. So it will be approximately equal to 1. So velocity is nothing but can be written as 2W by rho S CL, root of 2W by rho S CL. So rate of climb can be written as thrust divided by weight minus drag divided by weight into root of 2W by rho S CL. Lift equal to W cos gamma. When gamma is less than 30 degree, lift can be equated as equal to weight itself. So one of the weight, I replace it as lift. So thrust by weight minus drag by lift into root of 2W by rho S CL. This is your data. Now I simplify it further. Then we derive the condition for maximum lift. Okay. Rate of climb is equal to thrust by weight. Drag by weight, I will read as CD into half rho V square S. Lift, I replace it as CL into half rho V square S into root of 2W by rho S CL. So it will become rate of climb is equal to thrust by weight minus CD by CL. This CL, I'll take it on the top. So it is CL power minus 1 by 2 into root of 2W by rho S. So rate of climb, if I rewrite, it becomes thrust by weight minus CD into CL power minus 3 by 2, because this will become CL power minus 1, minus 1 minus 1 by 2 will become minus 3 by 2 into root of 2W by rho S. We know that CD is nothing but, according to drag polar equation, CD naught plus KCL square. So we know that this is the drag polar equation. So CD is equal to CD naught plus CDI. CDI can be written as KCL square, where K is nothing but 1 divided by pi AR, where AR is the aspect ratio, E is the Oswald efficiency factor. Substituting all these parameters here, what happens? Rate of climb can be rewritten as thrust by weight minus CD naught plus KCL square into CL power minus 3 by 2 into root of 2W by OS. If I further simplify, rate of climb is equal to thrust by weight minus CD naught into CL power minus 3 by 2 minus K into CL square minus CL square into CL power minus 3 by 2 will become, so CL square minus 3 by 2 will become CL power 1 by 2. Substitute. Yes. Somebody have some doubt?
So, yeah. In the third equation, shouldn't the CL negative 1 by 2 multiply with T by W also? You should have multiplied.
Yes. Sorry. Yeah, correct. Yeah. So this will become CL power 1 into root of 2W by OS. So for maximum rate of flight, here the only variable quantity is CL, the lift coefficient. So if I differentiate with respect to CL and equate it to 0, I will get the condition for maximum rate of flight. So if I differentiate this equation with respect to CL and equate it to 0, we get the condition for maximum rate of flight. So now first we differentiate first one. So thrust by weight.
Directly you can tell, please
Yeah,
don't
yeah,
differentiate. What will be the condition? They can
yeah.
differentiate.
Okay. So the condition will become thrust by weight into CL minus 3A plus BCL square equal to 0. Here A is, in some textbook they give it as A, but in most if it rewritten it is CD naught, that is parasite drag coefficient. B is nothing but K. In some textbook they given it as B, in some textbook they given it as K. So K is nothing but 1 divided by pi ER, equate to 0. Find out CL from this and substitute in all your equations. Then whatever we get corresponding to that, whatever we get the power required, that is drag into velocity we get, that is the condition. Then the power required will become minimum. So we know that drag is nothing but CD naught plus KCL square into root of 2W by rho S CL. So if I substitute for CL, which is obtained from this equation, here we get what is our power required minimum. So power required minimum depends upon CL, which is obtained from this equation. So this is the condition for maximum rate of climb of a jet engine aircraft. Yeah, Devans, you had some doubt.
No, sir, no, sir.
Autograph is the plot which is between velocity versus velocity. The horizontal component of velocity versus vertical component of velocity is defined as autograph. So the vertical axis is also velocity. The horizontal axis is also velocity. When you plot the same component in the vertical and horizontal component, then that kind of graphs are called as autograph. If you see, the maximum rate of climb is here because VV, the vertical component of velocity, which is nothing but V infinity sine gamma, max is your rate of climb max. Rate of climb max is nothing but this component should be maximum. So here if the vertical component of velocity is maximum when it is at the curve is at peak. But the climb angle will not be maximum at the same point. If you see the angle maximum, it is occurring at a point where it is tangent to this curve. If I draw a tangent to this curve here, from the horizontal axis, the angle it is forming is the maximum climb angle it can achieve. It is the maximum climb angle it can achieve, which means that climb angle maximum doesn't occurs at maximum rate of climb. Climb angle maximum occurs at a different condition rather than the maximum rate of climb condition. So the velocity at which the climb angle maximum occurs is also different, and the rate of climb maximum occurs is also different. So climb angle maximum occurs at a lower velocity compared to the rate of climb maximum velocity. Now we'll see what is the condition for maximum rate of climb. We know that V infinity sine gamma is nothing but thrust minus drag into velocity divided by weight. If I cancel V infinity, here we get gamma equal to sine inverse of thrust minus drag divided by weight. So gamma max occurs at a condition where drag is minimum. Gamma max occurs at a condition where drag is minimum. Drag minimum condition is nothing but CD naught equal to CDI. At this condition, the drag will be minimum. That is parasite drag coefficient equal to induced drag coefficient. That is when your drag is minimum. So, if you see rate of climb maximum occurred at a condition for piston engine aircraft at when power required is minimum. Same for jet engine aircraft, it has occurred at a different condition. But if you see the climb angle maximum, it is occurred at a condition where drag is minimum. Both the conditions are completely different. So climb angle maximum occurs at a different velocity, and rate of climb maximum occurs at a different velocity.
Sir,
What is the effect of weight on rate? Yes, Devan.
does it mean that the uh, climb angle at maximum velocity? Wait a minute, sorry. That the climb angle at maximum rate of climb has more drag than the at than the
Yeah, it
maximum
may be
climbing
more
velocity.
drag. Yeah, it will have more drag because if you see it, that is the condition where power required is minimum. It is not drag minimum condition. So, which means that here the power required only will become minimum, that rate of climb maximum. But here the drag is minimum. So you require rest thrust to overcome the drag. So drag into velocity is your power required. If the drag is minimum, if you see here, see this is where power required is minimum for piston engine aircraft. This is where drag is minimum. Drag into velocity is nothing but your power required. If drag only minimum doesn't indicate that power required is minimum. The velocity also, the flying velocity also should be minimum. Then only
Yeah.
power required minimum can be minimum. Understood, right?
Yes.
So there will be a difference. That's where. Okay. Now we'll see what is the effect of altitude on rate of climb. If you see, this is the power available at the sea level. This is the power required at sea level. As altitude increases, your power available decreases. As altitude increases, this is true for both the cases, jet engine or piston prop engine. As altitude increases, there is an empirical relation for power available, rho by rho naught into power available at sea level. So if I take this empirical relationship, what happens as altitude increases, density decreases. thereby power available also decreases. And as altitude increases, power required increases because the velocity required to achieve this lift will be more. So power required will be more. So as altitude increases, your power required. This dotted line indicates at a different at an higher altitude. This solid line indicates it is at sea level. So as altitude increases, your power available decreases and power required increases. So this is your excess power at an higher altitude. This is the excess power at sea level. So same is the case here. This is the excess power at sea level. This is the excess power at an altitude. So the excess power decreases. That means rate of climb is nothing but power available minus power required divided by weight. That is equal to excess power divided by weight. As altitude increases, excess power decreases, thereby rate of climb decreases for both jet engine aircraft and piston engine aircraft. We'll see what is the effect of weight on rate of climb. See, your engine performance depends, that is power available only depends upon the engine performance. It doesn't depend upon what is your weight of your aircraft. So power available remains same when weight increases also, when weight is decreases also. But power required, when weight increases, power required increases because your velocity should increase to maintain the same lift. Your velocity should be increased to maintain the same lift. When weight is increased, velocity also should increase. That means power required is nothing but drag into velocity. That means when lift increases, drag also increases. Since velocity increases, power required increases. So both the quantity increases, thereby power required also increases. So if you see, this is the excess power at less weight. This is the excess power when the weight got increased. Same is the case for jet engine aircraft also. So when the excess power got decreased, rate as weight increases, the excess power increases, thereby rate of climb decreases. Any doubt here? Now let's talk about what is called as absolute ceiling. As altitude keep on increasing, what happens? Power available keep on decreases. Power required keep on increases. At some point on the aircraft, where what happens? Your power available curve will just touch the power required curve. This is your power required curve. This is the power available curve. As altitude keep on increasing, what happens? Your excess power keeps on decreases. At some point, what happens? Your power available and power required, it will be tangent to the power required curve. Power available will be just tangent to the power required curve. So this point where the aircraft reaches where excess power is equal to 0, then that means rate of climb equal to 0 at that altitude. Not only rate of climb is 0, angle of climb also will be 0 at this point because we doesn't have any excess power. So we cannot climb at all. So that the angle of climb also will become 0. A steady level flight at only one particular velocity it is possible. At one particular velocity only it is possible. This is power versus velocity. At one particular velocity only, even steady level flight is possible because at this velocity, power available just equal to power required. So we can maintain just steady level flight. From this steady level flight, even the unaccelerated flight only possible. Accelerated flight is not possible. Because when it is got accelerated, let us assume it is got accelerated, it reached different velocity. When it is reached different velocity, what happens? Your power available is less than the power required. This is your power required curve. This is your power available curve. Power required is more than the power available. That means the aircraft only can glide down. The aircraft cannot pitch up. That is climb up. The aircraft can only glide down. So time taken to achieve this altitude is infinite. In aircraft, it is never possible to achieve this altitude. This altitude is called as absolute ceiling. For example, if you are trying to jump in your room, what happens? The maximum ceiling on the top of the house, up to that only you can jump. Beyond that, you cannot jump. Beyond that, if you are trying to jump, what happens? Your head hits that ceiling. Same way, when the aircraft is trying to climb further, the engine will get burned off. So the engine, then you lose your aircraft. So it is not possible to climb further. Yes, yes, sir. With the effect of weight, excess power decreases. Sorry, excess power decreases, so rate of climb decreases. Correct. So time taken to achieve this altitude is infinite. So it is not possible to achieve this altitude at any given time. So they have defined the practically possible maximum altitude to which the aircraft can climb. So for example, if you are 5 feet, you can possibly jump little more, 1 feet or 1.5 feet more, not more than that. Correct. Same thing for the aircraft. So there is a maximum possible altitude up to which the aircraft can climb. That altitude is defined as service ceiling. So service, since absolute ceiling is generally unattainable, there is a practically possible maximum altitude that is called as service ceiling, up to which the aircraft can climb. For piston engine aircraft, this altitude is defined as for piston engine aircraft, this altitude is at which rate of climb is just equal to 100 feet per minute, which is equal to 0.5 meter per second. When the rate of climb is equal to 0.5 meter per second or 100 feet per minute, that is where the maximum altitude you can fly a piston engine aircraft. Same way for a jet engine aircraft, the rate of climb when it is reached 500 feet per minute, which is approximately 2.5 meter per second, that is the maximum altitude at which jet engine is allowed to climb. If it is decreased beyond this 2.5 meter per second, then you have crossed the service ceiling. It mentions that you have crossed the service ceiling, which is not allowable as per given conditions. The aircraft should not be operated below this rate of climb conditions. So what happens is What is the effect of weight on absolute and service ceiling? Now, when weight increases, what happens? Already we have seen when weight increases, your excess power decreases. When excess power decreases, your rate of climb decreases. So, which means that when weight got increased, even at the lower altitude, you would have reached the rate of climb for any given aircraft to be equal to this value. So, that means even at the lower altitude itself, you would have reached absolute and service ceiling. So this was at when weight equal to 500 kg. This was your absolute and service ceiling. Let us assume this is your absolute ceiling. This is your service ceiling. When weight got increased to 600 kg for the aircraft, then your absolute ceiling and service ceiling got decreased because you will achieve that minimum rate of climb. That is the minimum rate of climb for a jet engine or piston engine, even at the lower altitude itself, because excess power got decreases as weight increases. With this climb performance is completed, we'll just look some of the great problems related to this topic. If you have any doubt, you can ask. Otherwise, we'll solve one or two problems related to this particular problems. GATE 2008. It's a linked question. Statement for the linked answer question. Linked question
One
is
doubt before
yes,
now. So you have
yes,
clarified that one of the
yes, yes,
misconception about that climb. Okay,
yes.
during the climb, the
Hmm.
thrust required will be uh, thrust required will be equal to drag plus weight component, right?
Yes.
That part
If you
you
see
have
here,
explained now. Because usually they write thrust equal to drag and that mistake.
if you see
Yeah,
here, thrust required is nothing but drag plus weight sign garment.
yeah.
So at least
Though
you
it is
should have this much thrust.
unaccelerated flight, yeah, but during climb, guys, the thrust is not exactly equal
Be
to
equal
drag.
to drag. You should have more thrust because a
You
component
require
of weight
more.
is also acting opposite to the direction of thrust. So you have to balance
Clear,
that thrust
everyone?
also.
Because based on this,
There
there
were
are
many
gate
questions
questions
asked in GATE.
in recent years. Yeah, please. Yeah, then continue. Thank you.
It's a linked question. GATE 2008, question number 76 and 77. This is the common data for that linked question. For piston propeller airplane weighing weight equal to 20,000 Newton. The given data, weight equal to 20,000 Newton.
Before that, we'll just check. Any doubt, guys? Whoever Shiva Puja, Saurabh, Sriza, Krutik, Devans, Chahit, Arushi, others.
No, sir.
Yeah. Shabrish, it's clear, right? Okay, then please continue.
Okay. The flight testing at 5 km pressure altitude in standard atmosphere gave the variation of power required versus true airspeed as shown in the figure below. So what they are given is they given the power required curve for sea level and at 5 km altitude. Okay. This the student forgot to label the airspeed axis. Some information which you doesn't require also given. Okay. The maximum climb rate at sea level was calculated to be so rate of climb maximum for sea level is given as 4 meter per second. Assume shaft power is independent of flight speed. Assume shaft power is independent of flight speed. For piston prop aircraft, it is assumed that shaft power is available is proportional to ambient density. So shaft power available is proportional to ambient density. This is the shaft power at sea level. This is the shaft power at any given altitude. This is the density at that given altitude. This is the density at sea level. This is what they are given here. If they are not given that also, we can assume this. Okay. Values of air density at sea level is sea level and 5 kilometer pressure altitude are given us. So at sea level, the density is 1.225 kilogram per meter cube. That is rho naught is equal to 1.225 kilogram per meter cube. Rho is equal to 0.74 kilogram per meter cube. These are the data given. Now we have to find out what is the they asked question number 76 to be equal to the maximum rate of climb achievable by this airplane at 5 kilometer altitude will be dash. Option A 1.65 meter per second. Option B 1.43 meter per second. Option C sorry, option B is 0.51 meter per second. Option C 1.43 meter per second. Option D 3.65 meter per second. I'll give a minute. Please try to solve it. Otherwise, I'll solve it. Anybody coming with an idea how to solve this problem? How to proceed this problem? We want to know what is rate of climb equal to. Rate of climb is nothing but power available minus power required divided by weight. The rate of climb maximum at sea level is given as 4 meter per second. From this graph, we know power required minimum even at sea level. Power required minimum at sea level is equal to power required at minimum at 5 kilometer altitude also. That is given as 5 into 10 power 4 watts. Generally, it's not so, but they are given power required minimum at 5 kilometer altitude will be way greater than power required minimum at sea level. But here in this plot, they are given both are to be equal. Power required minimum. This is the power required minimum at sea level. This is the power required minimum at a given altitude. So it is 5 into 10 power 4 watts. Substitute that here. So power available at sea level can be written as 4. If I take the weight on the other side, it is 4 into weight plus power required minimum. Weight is given as 20,000 Newton. So thereby power available, this is also given 5 into 10 power 4 watts. Weight is also given, which is 20,000 Newton. Substituting that, we get power available at sea level to be equal to 1,30,000 watts. Now we have to find out what is the power available at 5 kilometer altitude. So which is equal to rho at an altitude divided by rho at sea level into power available at sea level. What is the density at a given altitude? Which is 0.74, which is given. This is 1.225. That is what they are given. If they have not given also density at sea level, we have to know by heart, okay, which is 1.2256 kilogram per meter cube. Okay, since they are given 1.225, we are taking that only into 1,30,000 Newton, 30,000 watts, which we had calculated just now. So power available at 5 kilometer altitude is equal to 78,530.612 watts. This is the power available at 5 kilometer altitude. Now we have to calculate what is the rate of climb at that altitude. So rate of climb max at that altitude. So which is nothing but power available at that altitude minus power required minimum at that altitude divided by weight. So power available at that altitude is 78,530.612. Power required minimum at that altitude is 5 into 10 power 4 watts. Divided by weight is 20,000 Newton. So we get rate of climb to be equal to 1.426 meter per second, approximately equal to 1.43 meter per second. So option C is the correct answer. Any doubt here? Option C is the correct answer.
Yes, sir.
Devansh, it is clear, right?
Yes, sir.
In the linked question itself, question number 77. If during the maximum rate of climb at 5 kilometer altitude, the airplane was flying at an angle of attack of 4 degree, attitude angle of 5 degree, what was the equivalent airspeed of the airplane? Attitude angle means it is a pitch angle. So pitch angle can be written as, pitch angle is written as beta, which is alpha plus gamma, where alpha is the angle of attack, gamma is the climb angle, where beta is the pitch angle or attitude angle. So attitude angle they given it as 5 degree, angle of attack they given it as 4 degree. So gamma is equal to 1 degree, climb angle is equal to 1 degree. So rate of climb at max at that altitude is already we have calculated just now, 1.426 meter per second. 1.426, that is 43 meter per second, which is nothing but V infinity sine gamma equal to 1.43 meter per second. So gamma is equal to 1. Substituting that gamma equal to 1, we get V infinity to be equal to 1.43 divided by sine 1, sine 1 degree. We get the value to be 81.937 meter per second. This is the true airspeed of the airplane. This is the true airspeed because where we are accounted for density changes also into account. That is called as true airspeed. If the density changes is not taken into account, that is called as equivalent airspeed. So the equivalent airspeed is calculated as rho by rho naught of true, root of rho by rho naught of true airspeed. So rho we know, rho at that altitude is 0.74. Density at sea level is 1.225 into true airspeed is 81.937 meter per second. So the equivalent airspeed for this airplane is 63.684 meter per second, approximately 63.7 meters. This is your equivalent capacity. Option B is correct. Any doubt here? We'll solve two more problems, okay? And then we'll wind up. GATE 2012, question number 27. An aircraft has a steady rate of climb of 300 meter per second at sea level, 500 meter per second at the 2500 meter altitude. The time taken in second for this aircraft to climb from 500 meter to 3000 meter altitude is dash. We are going to take one assumption that we know that rate of climb decreases with respect to altitude. We know that rate of climb decreases with respect to altitude because excess power decreases. So we'll assume here that it is linearly decreasing with respect to altitude. So if I draw this plot, rate of climb versus altitude, rate of climb versus altitude. So at sea level, which is at 0 kilometer altitude, so the rate of climb was 300 meter per second. As altitude increases, the rate of climb got decreased. When the altitude was 2500 meter, the rate of climb was 150 meter per second. We know, like straight line equation, y equal to mx plus c. Here y is nothing but rate of climb. M is the slope, which is negative here, where x is nothing but the altitude plus c. C is the value of y at 0 kilometer. So first we have to find out what is the slope. Rate of climb at 2500 meter minus rate of climb at sea level divided by the altitude difference, that is 2500 minus 0. So rate of climb at 2500 meter is 150. Rate of climb at sea level is 300 divided by 2500. That is equal to the slope is minus 0.06, because rate of climb is in meter per second. This is in meter, so it is in per second. So if I substitute in this equation, rate of climb can be written as minus 0.06 h plus c, constant at x equal to 0 is 300. So 300. This is your rate of climb equation. We know that rate of climb is nothing but rate of change of altitude with respect to time. Rate of change of altitude with respect to time. Now, what happens? We want to find out what is the total time taken. That is equal to dh by rate of climb. So, when the altitude was h1, time taken was t1. When altitude is h2, time taken is t2. So, the total time del t they asked us to find out, which is taken from 500 meter altitude to 3000 meter altitude. Time taken to find out from 500 meter to 3000 meter altitude. dH by rate of climb equation we know, which is 300 minus 0.06 h. So this is in the form of dx by a minus bx. So if I integrate this, we can rewrite this as minus 1 by b into ln of a minus bx. This is the integration formula. Same way, if I rewrite minus 1 divided by 0.06 into ln of 300 minus 0.06 h 3500. If I substitute the limits, we will get what is the total time taken, which is 13.515 seconds. The total time taken is 13.515 seconds. Now, they asked what is the time taken to climb from 500 meter to 3000 meter. They given the value for 500 meter and sea level and 2500 meter, but they asked us to find out what is the time taken from 500 meter to 3000 meter. Rija, is that clear? So answer is 13.515 seconds. We'll solve one final problem and we'll end this section. Okay. Any doubt here? Anybody? Any doubt?
No, sir.
Yes,
No, sir.
Devansh. No problem. Okay, we'll wind up now. Okay. Anybody, any doubt you can ask? Or any comments on improvements you can also tell. I hope everybody understood this section. Thank you.
Srija is saying something H2 equal to
No, I have
2500.
explained that. I have explained that.
Okay. Okay. So, guys, any other comments? Anything? Okay, so this is just simple, glance or crisp of what we, teach and how we teach.
Basically,
So,
we
are
teach
you
from
all?
basic.
Yeah. This is just like one demo class. Otherwise, we start from this atmosphere, where you guys understand how these properties vary with altitude and different atmospheric layers and other things. So, guys, you all are comfortable with our pace of teaching and the way we teach in interactive classes, guys?
Yes, sir.
Okay. All right. Arushi, since you are non-aero background students, how are you feeling? So we have two more demo classes. Okay. Now, since the previous demo classes also will share the recording of. So no doubt, guys, right? No further doubt. Yes or no?
No, sir.
All right. Okay then, guys. Thank you for joining this session and see you all in tomorrow's and Saturday's demo classes, and then Sunday we will have first regular class. Okay. Thank you all, guys.